class. Okay, so we're going to talk about waves. Now, waves are a little bit difficult to define precisely what they are because there's so many different types of waves. Some examples of waves, we can have like a string. So say you have a string and you grab one end and just shake it up and down, you'll create a wave that travels down the string. Sound. That's just waves in the air. So sounds are caused by pressure differences in the air that travel from the source of the sound. It causes a disturbance which changes a pressure, and that disturbance travels and your ears can detect that. And so these are waves in air. So string, obviously there'd be a wave in the string itself. Water, obviously. So we have waves in water. You can see those on the surface of water. See, what else do we have? We can have waves in solids as well. Let's just look at an example. Earthquake. So that'd be like a wave in the earth, like the crust. And actually, something significant, the wave also travels through the inner layers of the earth, like the mantle and core as well. And so very different things we're talking about here, but they have some similar properties. There's another one here we're going to call light. Now, we're not going to talk about light until the next class in the sequence, but light is made of electric and magnetic fields that oscillate and travel. And so it's called an electromagnetic wave. And one more I should probably mention, this has been getting some attention lately, gravity waves. These were predicted in 1916 by Einstein. Our current theory of gravity is due to Einstein. He replaced Newton's theory, and one consequence is this idea of gravity waves. And gravity, as we know, is an extremely weak force. And so when Einstein predicted them, he figured they would never actually be detected. That's extremely difficult to detect. But I think it was in 2015 that gravity waves were first actually measured. We have several gravitational wave observatories now that are all connected to each other. And extremely difficult, but they can now be detected. Now, I should point out that there was actually very strong evidence for gravity waves before we were able to detect them. And that's because one property that all these waves have in common is that they carry energy. And back in the 1970s, these astronomers discovered these two neutron stars that were orbiting around each other. So very dense stars. And they were orbiting very close to each other. So they're spinning around. And they were able to measure the period of the rotation. These neutron stars are emitting radiation. And due to something we're going to talk about later called the Doppler effect, like if the star is moving towards you, the frequency of the radiation is going to be affected, or if it's moving away from you. And so when they were looking at these neutron stars, the radiation is directed by magnetic fields in kind of like a beam, and this beam just happened to pass by Earth, and so every time it rotated, we could see this burst of energy. And these are extremely dense and rapidly rotating objects, and as we learned from Chapter 9, when you have an object with a lot of angular momentum, it's very difficult to change that. And so it'd be very difficult for the spinning of the neutron star to change significantly, but they noticed very significant changes in the frequency, and they correctly identified the reason is that this neutron star they were detecting was orbiting around another one that they just couldn't see. And because of the Doppler effect, the frequency would increase and decrease every time it cycled. It's moving towards us and then away from us. And so they were able to determine, based on how often the frequency was being affected, they can measure the period of the motion of the orbit of this star. And because they're such dense objects and they're close together, they emit a significant amount of gravitational energy, or energy in the form of gravitational waves. And so that should affect their orbit. And they were able to correctly identify how the orbit should decay. And yeah, it's kind of interesting to see a plot of the measured period of rotation and the actual data, like the theoretical prediction based on Einstein's theory of gravity, and what they actually measured, and it just lined up perfectly. So there's very strong evidence for the existence of gravitational waves, even going back to the 1970s. Those two astronomers won a Nobel Prize for that. But yeah, the first direct observation was, I think, 2015 or so, somewhere around there. Okay, so again, what does a wave on a string have to do with a gravity wave? These seem like extremely radically different things. But all waves they have certain properties in common. A wave, we can say, is a disturbance that carries energy. Let's just say that. Not a very precise definition. If you want to get precise, you have to talk about, mathematically describing waves and things like that. We're not going to get too much into that in this class. So we're just going to say it's a disturbance that carries energy. So if you have a wave on a string, the disturbance, you oscillate one end, you create these pulses, and of course they can affect things. If that pulse hits something, you can move it. That takes energy. Sound waves carry energy. If they didn't carry energy, you wouldn't hear anything because they couldn't interact with your ears. Water waves, they can definitely carry a lot of energy. Same with earthquakes. Not so much gravity, but it's still there. And light obviously carries a significant amount of energy as well. And I say obviously because we get all our energy from the sun. Either directly or indirectly, it almost all comes from the sun. We have a little bit of internal energy due to the Earth having this molten core, but most of the energy that we use comes from sunlight. So yeah, these are all examples of waves. And basically think of a wave as some disturbance that carries energy from one point to another. Now, let's look at a wave on a string. Let's say I have a string here, and I grab the end and just lift it up and down and create a pulse. Actually, let's say I have an actual string here, and let's say I take a marker and place a dot somewhere on the string. And let's just say I create a pulse that looks like this. So this is our wave. And it's moving to the right at a certain speed. And most waves have some medium that the disturbance is in. Like in this case, the medium is just the string. Sound waves, the medium is the air. But here it's just the string, the medium is the string itself. And so the wave is moving to the right. What's going to happen, like after the wave passes, where is this red dot going to be? And well, it's going to be right where it was. So a wave is a disturbance in a medium that travels, but the medium itself does not generally travel. I mean, obviously it could. You can move the string, but we'll say that forget the motion of the string. The wave is moving through the string, but the medium itself is not overall affected by this. Like this red dot, we place it here, it's not going to move down along with the wave. Now the wave passes, it's going to go up and down. You can kind of see this with water waves. If you look at an object floating in the water, when waves pass, they tend to move mostly just up and down as the wave passes. They don't get carried along with the wave too much. So this is one example of a wave. And I'm going to look at another one. Let's say we have a spring. So a great example of a spring would be a slinky. So yeah, let's say we have a slinky. And let's say you grab the end and oscillate it back and forth this way. So you can take a slinky and oscillate it back and forth this way, and it'll create waves like this. But what if we take this and oscillate it back and forth? Let's say we push this spring inwards. Basically, you can think of it, this coil is going to move towards this other coil. So these coils are getting closer together, but that's going to push this coil into the next one. And so we get this compression that happens. And this compression travels down the slinky. And so if we look at one, let's say we painted one of these coils red, what's going to happen to this coil as this wave passes through the slinky. So the motion of the coil, like in this case, we're going to make a more, let's change this wave to be, so let's say we just keep oscillating this end back and forth. What's going to happen when the wave passes the that red dot? Well, the red dot is going to move up and down. Well, first it'll move down, and then it's going to move up. So it's going to move like this. Where if you compare it to this example with like a spring or a slinky, when this coil moves closer to this one, it's going to push it to the side, and then it's going to come back. And so it's going to oscillate back and forth like this. And so these are very different types of waves. We call this a transverse wave. And the characteristic of a transverse wave is that the disturbance in the medium, causes a displacement in the medium that's perpendicular to the direction of the wave. And in this case, the disturbance is in the direction. It's parallel to the direction of the wave. We call this a longitudinal wave. So transverse and longitudinal, those are the two basic types of waves. Now, I should point out that waves are actually an extremely complicated subject. Like when you study physics, everything is kind of either a particle or a wave. We have like atoms are particles. Things like light is a wave. But we learned in the 20th century that the line between particles and waves gets kind of blurry. And in a lot of cases, we even treat particles themselves as waves. So we're talking about a very difficult subject. And these are just the fundamental ideas, but don't expect these to carry over perfectly to the real world. Like if you look at a wave on the surface of water, like say you drop a stone in a lake and watch the wave move out, if you look at the molecules in the water as the wave passes by, they actually go through kind of like a circular motion as the wave passes by. So not every wave is going to behave perfectly like one of these two simplified examples. But it's actually important to define these anyways, even if you're going to go into like very complicated problems, because in the case of a circular wave, we can actually consider it just like we have vectors. We can break vectors into components. we can kind of do the same with these circular waves, where it has a transverse component that goes up and down, and a longitudinal component that goes back and forth. But in many cases, real waves actually do have like one of these two to a very good approximation. And one reason why it's important to distinguish these, there's a couple reasons, but one is different mediums can support different types of waves. Like a wave on a string can only support transverse waves. If you have a string lying flat and you want to make a compression wave, like a longitudinal wave, like if you push this end of the string, it's just going to crumple the string. It's not going to create this pulse that travels down it. So like a string can only handle a transverse wave. A slinky can handle both. You can grab a slinky and oscillate it so that it makes that wave-like motion, or you can compress it and cause this longitudinal motion. And earthquakes, this is actually a very important example because we can learn a lot by studying earthquakes. So we have the seismic station that can detect waves, and the Earth is made out of layers, where we have, like in the middle there's a core, and then the mantle, and then the crust, which is what we live on. And the crust is this very, very thin layer. And I've read kind of a good analogy. If like the Earth was the size of an apple, the crust would actually be thinner than the skin of the apple. So crust is a very thin layer. But the different layers of the Earth can support different types of waves. And so let's say here's the Earth, and there's an earthquake that happens here. Let's say earthquake happens here, and if there's a seismic station right next to it, say A, and say B and C, say we have different seismic stations that detect this earthquake, like the wave getting to A, it can travel through the crust, and so we can get all different types of waves. But to get to B, it has to pass through these other layers of the Earth, and I think the mantle cannot handle, it's more of like a liquid, it can't handle transverse. I don't know if I'd call it a liquid, but it doesn't support these transverse waves. So an observer at A can see transverse and longitudinal waves, and an observer at B or C, they're not going to see these. So here we could have, like, say, transverse and longitudinal. Here we're just going to see longitudinal waves, the ones that pass through the mantle. And then if it has to pass through the core, there's going to be like a shadow where they can't pass through the core, or they'll be affected by it at least. So it can create this shadow. And so just by looking at the waves at different seismic stations, we can learn a lot about what's going on inside the Earth, like all these different layers of the Earth. And that's very important because we have no real access to anything except the crust of the Earth. We've never experienced anything directly. Now, they've tried digging holes all the way down to the mantle. And in the 60s, they actually came very close. They had a ship that was just digging a huge hole into the crust of the Earth under the water, trying to get to the mantle. And this ship, it was actually capable of doing it, but it ran into some technical issues. It's an extremely complicated thing. But they're still trying to do that. And eventually they will succeed and dig a hole to the mantle. But we haven't done that yet. Everything we know about the interior of the Earth comes from these indirect measurements like earthquakes. And also kind of modeling like how planets form. We can make guesses about what's going on inside. But this studying how waves propagate through different mediums. Other things can be affected, like the speed of a wave we'll talk about later. The speed of a wave depends on the density of the material, and the density changes. So like if a wave had to travel to station B, we could get some idea of what the density is by just looking at how long it took the wave to travel. And the more stations we have detecting this, we get more information. And so, yeah, just that's one of the main reasons, I think, why transverse and longitudinal waves are so important. It's different means of transmission. And some mediums can only carry certain types of waves. Now, most of these have a medium. Like even gravity, the medium for gravitational waves is just space itself. That's something very interesting about Einstein's theory of gravity. Einstein's theory basically says that like the Earth is moving around the sun, it's not that the sun is actually pulling on the Earth. The sun isn't doing anything to the Earth itself. What Einstein said is that that mass warps the space around it. It alters the geometry of the space around it so that it's not the familiar Euclidean geometry we're used to. And so what the sun is doing is it's altering the space around it, and we're moving through this warped space. That's why we're moving around the sun. There's no real connection between the Earth and the sun. We're moving in this elliptical orbit because space is warped and causing us to do that. And certain astronomical events can actually create ripples in space that are now detectable. So basically all of these have a medium except for light itself. I guess you could say space, they travel through empty space, but they can, that's basically a vacuum. And so yeah, light can travel through a vacuum. It's made out of electromagnetic waves, and they can travel through vacuum. Okay, so what I want to do now is talk about a mathematical description of a wave. So let's erase this. Just, again, it's difficult to define precisely because there's so many types of waves. So on this page, the basic idea of a wave is that it is a disturbance that carries energy from one place to another. And there's two main types, transverse and longitudinal waves. So let's move on from there, and let's talk about how we can describe a wave mathematically. So let me draw. Now, waves, let me draw like a classic wave, which we can describe with a sine or a cosine. I'm actually going to describe it as a cosine. So let's say here's a wave. And say this is a picture of a wave. So here we have, say, x and y. So this is a picture of like a wave in space. However, the wave is moving. Let's say it's moving to the right with a speed v. So again, this would just be what the wave looks like at one moment in time. If you look at a different time, it's going to be different because the whole wave, this whole pattern has shifted. So we can visualize this as like a wave on a string, for example. And again, this is just at one point in time. This is what the wave looks like. But let's say we know it's moving to the right with a speed v. And let's look at a point on the wave. Oh, we can describe this as a cosine curve. So the wave itself is a function of both x and time, and t. So really what we want to come up with is something like this. Say y is the amplitude of the wave. That's going to depend on both the x coordinate. Like if you say x equals whatever this value is, y is down here, a different x value, you get a different y value. So the amplitude is definitely a function of x, but it's also a function of time because the whole thing is moving. But we're going to look, let's start by looking at one moment in time, which we'll call t equals 0. So the amplitude is a function of x right now. And we can describe this by a cosine. The simplest thing we could do is just say y equals cosine of x, but we don't know, like we can have waves of different sizes. So we need to give it an amplitude. Okay, but also just saying cosine of x, that would mean this wave would have a specific length, basically. Because cosine of x, you'd have to go through, when x equals 2 pi radians, then you've completed one cycle. And so that would fix the wavelength, but waves can have different wavelengths. So we define the wavelength to be like from one peak to the next. So that's our wavelength there. But again, we can have waves of different wavelengths, and so we need to be able to take that into account. And so what we can do, let's put something in front of that. Let's say y equals a times cosine of kx. And so if we adjust k, then we're either going to stretch this wave out, give it a longer wavelength, or compress it and give it a shorter wavelength. I just want to check the notes to see if that's what I called it. Initially, in the notes I called it AX. A lowercase a, so I'll stick with that. K would be a better variable to use there because that actually has a name. It's called the wave number, but that's fine. Okay, so for a particular wave, how do we find what this constant is? And I mentioned it should depend on the wavelength. Like if we just have cosine of x, let's compare. Let's say that this function is cosine of x. So this is y equals cosine of x. What happens if we replace that with 2x? What that's going to do is it's going to shrink, or it's going to make the wave look something like this. It's going to give it a shorter wavelength. So this red one is y equals cosine 2x. Now you might wonder, why did it shrink the wave? Well, think about, you complete a cycle when after this cosine is equal to 2 pi, that's when you complete a cycle. So if you just have x, you'd have to go to 2 pi to complete a cycle. Now if we have cosine of 2x, x would be, when x is equal to pi, then we've completed a cycle. And so, yeah, the wavelength is only half of what it would be in this case. So here we have to go through 2 pi to complete a cycle. Here x has to just go to pi to complete a cycle. So we can fit twice as many waves in the same length if we put that 2 in front. So if this number is high, that means we have a compact wave with a small wavelength. Where if we put like 1/2 x, that stretches it out the other way. And since this constant can be anything, we can describe a wave of any wavelength. So let's see how it relates to the wave more precisely. Well, we know if x equals 0, we know this point, x equals 0, and the amplitude here is a. So that point has coordinates 0, a. And at this point, we've completed a cycle. And so we're back to that same amplitude a, but now the x-coordinate is lambda. And so this point here has coordinates lambda, comma a. So let's plug that in. The y-coordinate is a, and that's equal to a cosine lowercase a times lambda. And so cosine of a times lambda is 1. Now, when does cosine equal 1? Well, that's when, let's just say that this is theta. This, whatever's in the parentheses. If theta is 0, cosine's 1, well, that's this point here. At 2 pi, we're back to 1, that's this point. And then this point would be 4 pi. But this point right here, when you travel one wavelength, we know that whatever's in the parentheses is 2 pi. So we have a times lambda equals 2 pi, or a is 2 pi over lambda. So what we have now so we replace a with 2 pi over lambda. And so we've now described this wave at one moment in time. So we got the space part at a single moment in time. And yeah, we wrote it in terms of its wavelength. So now what we have to do is take the time dependence into account. But before we do this, there's another really important thing. Let's look at this point. You know, it's moving with this disturbance is moving with a velocity v. Let's look at the motion of the wave. Like this crest of the wave here is going to move across, and after some time, it's going to be here. Now, the time it takes to reach this point is a period, because we're talking about cyclic motion here. When the wave goes through one cycle, it's back to its original amplitude. And in that time, it moved a distance equal to one wavelength. So just using distance as speed times time, the distance we traveled is the wavelength, and that's equal to the speed of the wave times the time that it took to do that, which is the period. How long did it take to complete one cycle? So we have this relation here. Now remember, we defined frequency to be 1 over the period. We can just as well say the period is 1 over the frequency. So we have the speed of a wave, or the wavelength, sorry, is the speed divided by the frequency. Oh, I probably should have mentioned this symbol here, that's a Greek letter lambda. That's what we use for wavelength, that's standard. Okay, now, yeah, wavelength, v times a period. Period is 1 over the frequency. So if we multiply the frequency, we get this very important result. The speed of a wave is equal to its frequency times its wavelength. It's actually a very easy formula to remember as well, because frequency is measured in hertz, which are inverse seconds. Wavelength are measured in meters, so we get units of meters per second. So you can think just from dimensional analysis, very easy to remember that equation. Although you don't have to, it's on the equation sheet. Okay, so the last step I want to do is take the time dependence into account. Now I might need some room here, so what I'm going to do is erase these bottom two lines, and let's just do this. We'll put the result here. Actually, I want to do this a little bit differently. Okay, so 2 pi over lambda, that's a constant, and then x is our variable. Okay, now what does time have to do with this? How would time affect this? Well, the shape of the wave is not going to be affected by time. Like the wave is going to move to the right, but like if you take a picture later, this whole thing is going to look the same, it's just moved down farther. So it's still going to look like this cosine, but it's going to be shifted to the right. And so after a time t, the amount this wave has been shifted is going to be equal to the distance it traveled. Let's call that delta for now. So it travels a distance vt. After some arbitrary time t, the entire pattern shifts this distance. However fast it's going, times whatever time we're looking at here. And so what we want to do is we want to take this pattern and shift it. Now, how do we do that? Let's look at I like looking at a simple example. Let's say we have a nice parabola. Say we have y equals x squared. Now what if we want to take this pattern and shift it to the right 1 unit? So we get, say, this graph. So what is the equation for this red parabola if it just shifted over 1 unit? And what you do is to shift the graph over 1 unit to the right, you replace x with x minus 1. If you're shifting it to the right, you replace x with x minus 1. So this would be y equals x minus 1 squared. Now, why minus if we're shifting it to the right? Well, if we plug x equals 0 in, we should get 0. Now, over here, if we want 0 for y, we have to plug x equals 1 in to get 0. So it's kind of backwards of what you might intuitively expect. We use a minus to shift the pattern to the right. So now going back here, if we want to shift this pattern, what we want to do is to take time into account. This whole pattern is moving to the right, and the distance it moves is v times t. So to shift it that far to the right, we're going to replace x with x minus vt. So that'll shift the whole pattern to the right. So let's do that. So now we have y as a function of position and time. So that's a cosine. Now we have 2 pi over lambda x minus vt. And we want to clean this up a little bit. But this is, in a sense, we could just leave it like this and we're done, but I want to clean it up. So first thing, let's distribute this 2 pi over lambda. So we have 2 pi over lambda times x. And then over here we have minus 2 pi v over lambda times t. Okay. Now, v over lambda. So let's look at this equation. If we have v is equal to the frequency times the wavelength, if we divide by the wavelength, v over lambda is equal to the frequency. So here we have 2 pi times the frequency times time. Now remember, I'm just going to erase this. So remember that the angular frequency is 2 pi times the frequency. So here we have 2 pi ft, or this whole thing just becomes omega t. So we can replace this with a cosine, and now we have 2 pi over lambda times x minus omega t. Now it's 2 pi over lambda. That is a name that's called the wave number. And I'm not quite sure why, but I didn't include it in the notes. I probably should have. We'll just do that here, even though it's not in the notes. So k is 2 pi over lambda. That's called the wave number. So then we can simplify this even more. So we have y as a function of position and time. It is a cosine kx minus omega t, where k is 2 pi over the wavelength, and omega is 2 pi times the frequency. And that's kind of our final form. However, one thing, let's go to the unit circle again. Let's say we have an angle theta. So an angle theta, remember the x-coordinate of that point has, that would just be cosine. What if we have minus theta? What if we just go theta in the other direction? Well, it's obvious from symmetry that these x-coordinates are going to be the same. And so, not exactly a mathematical proof, but good enough. Cosine of minus theta is equal to cosine of theta. And so what we can do is we can just multiply this by -1 and reverse the direction if we like. So we could also write it as a cosine omega t minus kx. You can write it whichever way you like. Okay. Now one thing, this describes a wave moving to the right. If we had a wave moving to the left, we would do everything the same, except instead of replacing x with x minus vt, we'd replace it with x plus vt. So our final form, I need room to write it. Here, we'll just write it. To erase everything. So a final form, the amplitude is a function of position and time. We have A for amplitude, and then cosine. We can write this as kx plus or minus omega t. So plus would be a wave moving to the left, minus would be a wave moving to the right. So we can describe a wave moving in either direction. Okay, see how long this one is. There's one more thing we want to talk about, and that is the speed of a wave. That's something that's actually pretty interesting. Say we have like a metal bar. And you take a hammer and hit the bar. You're going to create a wave, like a compression wave, that travels down the bar. Now, how fast is that wave going to move? Well, it depends on certain things, but the interesting thing is, it does not depend on how hard you hit it. If you just tap it, you'll create a wave traveling through this bar, or if you really pound on it with a hammer, the wave's going to travel the same speed. Kind of interesting. Maybe not an intuitive result, but that's the way it works. Now, the waves will be different. If you really pound it with a hammer, you'll have the amplitude of the wave will be greater. And we're going to see like the amplitude of a wave is a measure of how much energy it has. But the speed of a wave depends on the properties of the medium, not what created the wave. So the wave is a disturbance. Once you have a wave traveling through a medium, The speed it travels only depends on the medium. It does not depend on the source. Now, how do you find the speed of a wave? Like, say we want to do this from first principles. Like, say we have a wave on a string. How would we find the speed of this wave? You can do this with Newtonian mechanics. We're not going to do that. And it's actually a fairly complicated thing to show, the speed of a wave. And there's all sorts of different types of waves. Waves on strings, waves traveling through water or air, waves traveling through solids, and actually figuring out like how fast the wave should be moving. In general, that is a pretty complicated thing. So what we're going to do, I want to look at just a wave on a string, and we're not going to derive the result. We're just going to take two experimental facts. The speed of the wave depends on the tension in the string, and something called the linear mass density. So these two factors determine the wave, the speed of the wave on the string. Now tension, measured in newtons. Now what is linear mass density? We use lambda for mass density. Linear mass density, kind of unfortunate because we're using that for wavelength, but we can always tell from the context which one we're talking about. So this is the linear mass density. And we say that's defined as the mass over the length. So, for a string, and the basic SI units would be like kilograms per meter. But strings usually don't weigh, in the kilograms, so we probably use like grams per meter, or even like milligrams or micrograms or something. But the basic SI units would be kilograms per meter. And what we're going to do is we're going to say, just knowing that these are the two factors that determine the speed of the wave, how can we arrange them so that we're going to get the right units? Because we have to get the right units. So let's say that the speed of the wave, let's say that that's going to be tension to some power, we'll call it A, times the mass density. Sorry, I just realized I used the wrong. I think in this class, let me just check the notes. I think we used mu actually for mass density. Seen both, but yeah, sorry. Well, less confusion this way. We're using this Greek letter mu for mass density. Again, same thing we use for friction, unlikely to cause any actual confusion. So how do we figure out what these exponents are? And if we do figure out what these exponents are, does that mean we found the wave, the speed of the wave on a string? No, because we could put something dimensionless in front of that. Like we could put 1 billion in front and that still has the right dimensions, but very different results. But we're going to do this anyways, just to see what it should look like. So we're going to break this down to our base SI units. So we have kilogram, tension is kilogram meters per second squared, which we're raising to the power A. And mass density is kilograms per meter, which we're raising to the power B. And what we should get out of this, a speed should be a meter per second. So we just have to find these exponents, A and B, that'll give us the right units, meters per second. So we can clean this up a little bit. I'm going to break it into pieces first. exponent A applies to everything. So we have kilograms to the power A, meters to the power A, and because seconds are squared, we have seconds to the power 2A. And then here we have kilograms to the power B over meters to the power of B. And I'm going to do one more thing. I'm going to combine all these terms now. Now on the left, I'm going to write this in kind of a strange way. But hopefully you can see that this is equivalent to this. Forget the kilogram for a minute. Meter by itself, we can just as well say it's meter to the first power. And since second is in the denominator, we can write it as second to the -1 power. But what about kilogram? Why are we putting it there when it doesn't actually exist over here? Remember, anything raised to the 0th power is 1. So that won't affect anything. And we're just doing that because we have kilograms on the right. So basically what this means is that these kilograms have to cancel each other out. So we can write it this way. And on the right, then we have kilograms. Here, kilograms to the A times kilograms to the B. That's kilograms to the A plus B. And then if we go to meters, we have meters to the A divided by meters to the B. That's A minus B. And seconds only shows up once. And we're going to write that seconds to the power minus 2A because it's in the denominator. And so now just by comparing these, we get this set of equations. We have A plus B has to be equal to 0. I don't think we need this wave anymore. So let's write this down. We have A plus B has to equal 0. Here, looking at meters, A minus B has to equal 1. Because meters is raised to the first power. And from comparing these, we say that 2A has to equal 1. Because here they're both negative. So -1 equals minus 2A, or 1 equals 2A. And we can immediately solve for A. A is equal to 1/2. And that means B has to be equal to minus 1/2. Because, A minus B, 1/2 minus minus 1/2, that's 1/2 plus 1/2, which is 1. Or if we add A plus B, 1/2 and minus 1/2, they cancel out, we get 0. So we found A and B. So now we can say our velocity is T to the 1/2 times the mass density to the minus 1/2. And finally, we're going to write it, maybe I'm going to erase this equals sign. Oh, here. All we can really say is that the speed is proportional to this. We don't know that it's exactly equal to this. So our final result, we can combine or kind of simplify it and write it like this. So T to the 1/2, that's the square root of T. Mu to the minus 1/2, that's 1 over the square root of mu. And so we can just combine it, the square root of T over mu. And so we know that the speed of a wave on a string should look like this. But what is it exactly? Well, it turns out that this is actually the right answer. So just by doing this process called dimensional analysis, this is an extremely useful thing, way more useful than you might expect. But yeah, we get the result that for a wave on a string, the proportionality constant is just 1. So speed is just the tension, the square root of the tension over the linear mass density. So again, we didn't derive that. Well, we showed it had to look something like this. And yeah, if we just put the 1 in front, we can take that as an experimental fact. Now, it is possible to derive this result using Newton's laws of motion. but it's actually a fairly complicated thing to do. It's something that would be kind of questionable to do in the calculus-based version of this class. I mean, you could do it, but it's one of those things, maybe it's like, just put it in the notes or it's in the book where you can read it, but we're not going to go over it in class just for time reasons. Now, the other types of waves, we're not going to, here, I'll just show you, I'll write them down. So, wave on a string, we get and the next is wave in a gas. Now let's say, to start with, let's say we have like a pure gas, just like pure helium or hydrogen or neon or something. And I'm going to write down this formula. Gamma kT over m. That'd be the speed of a wave in a gas. Now, that might not mean much because what are these things? Well, gamma is a number that depends on the type of gas. Now, what do I mean by type? You could have something like helium, which is a noble gas. And it doesn't bond with other things. So if you have a gas of helium, it's just a bunch of helium atoms floating around. That's a monatomic gas. And then if you have something like a gas of hydrogen, that's a diatomic gas. And this gamma depends on whether it's monatomic or diatomic. And of course, molecules can get more complicated. But gamma is just a number that depends on the type of gas. And it's 5/3 for an ideal monatomic gas and 7/5 for a diatomic gas. You don't need to know where those numbers come from, or you certainly don't need to remember them. Now, K is something called Boltzmann's constant. I think that's on the equation sheet. It's a very important constant. It's 1.38 times 10 to the minus 23rd joules per Kelvin. What is a Kelvin? That's a measure of temperature, which we'll get to in a moment. Now, Boltzmann was one of the leading scientists of his time. Unfortunately, people didn't accept his work because he had this crazy idea that there were these things called atoms that existed. And in the 1800s, that was very much disputed. And so, apparently, I'm not 100% sure about this, but they say he got depressed because no one accepted his work. And so he wound up killing himself as a result. And it was very shortly after that that atoms became universally accepted. But yeah, Boltzmann did some very, very brilliant work dealing with, it's called like the kinetic theory of gases, where you treat a gas as a bunch of particles moving around and hitting things. And yeah, he did some very pioneering work in that. Let's get to T. Now, T is the absolute temperature. Now, what does this absolute temperature mean? Well, you can't use Fahrenheit. Say it's really cold out and the temperature is minus 10 degrees Fahrenheit. If you plug in negative 10, now you're taking the square root of a negative number. That's a problem. So what this means, again, if you take the next class in the sequence, you take 122, you learn that there's kind of like a lowest temperature. That you can if you cool things down, there's a limiting temperature that you can reach by cooling things down. Or, well, you can't reach it. You can get close to it, but you can never quite reach it. And that's called absolute zero. And there is a temperature scale based on absolute zero called the Kelvin scale. So our Boltzmann's constant, the units were joules per Kelvin. And then if you multiply it by temperature, the temperatures cancel out. But it has to be a temperature based on this absolute zero. And finally, m is the mass of a single particle. So if you have, now that particle could be an atom or a molecule. yeah, like if you have helium, that's a monatomic gas, so that would M would just be the mass of a single atom of helium, or hydrogen. Yeah, helium. Now hydrogen, that one is diatomic. Two hydrogen atoms are going to combine to form a molecule of H2. And so that'd be like one particle of the gas, and so M would be the mass of a hydrogen molecule, which would be two hydrogen atoms. Now again, you don't need to know, like if I gave you a problem and just said a hydrogen gas, I should tell you whether or not that's monatomic or diatomic, or give you the formula like this so you can tell very easily. If I forgot and you see this on a test, definitely let me know. That you can ask that during a test if you don't know if it's monatomic or diatomic. Then ask. Okay, so that's it for a gas, except for one thing. This is for a pure gas. But what if you take like air that is made out of nitrogen and oxygen and carbon dioxide, probably some other things as well, but I think those are the main three. And, what would M be for that? And I give an example, I don't want to go over it, but you take like the fraction, here I'll write down, you take like the average, you just replace M with the average. So let's just say we have two gases. Where F1 and F2 are the fractions. So let's say you had a gas that was like 40% helium and 60% oxygen. Then F1, we'll say mass or particle 1 is helium. So F1 would be 0.4. 40% is 0.4, and F2 would be 0.6. So you would just plug in like 0.4 times M1 plus 0.6 times M2, and that would give you like the average mass, and then you'd plug that in instead. Okay, I think there's two more we're going to look at. Sorry, this video's carrying on a little bit longer than I wanted to, but we're almost done. So for solids, we've got this. Where this capital Y, this is something called Young's modulus. Young was a physicist in the, he was more like just a genius in the 1800s. He was a physicist and a mathematician, and you might have heard of the Rosetta Stone, like that Egyptian tablet that I guess that stone had like Egyptian and Greek on it or something like that, writing, and so that's how they're able to translate hieroglyphics, because they had something containing both, like a known language and an unknown. And Young was one of the people that actually figured that out. So he was kind of like this all-around genius. Math and science, and then things like languages as well. So Young's modulus, basically what that is, you can almost think of this as like a spring constant, except we're talking about, like, say you have a steel beam that's supporting something like the ceiling of a building. So you have this massive weight here, and you might think like steel, that's a pretty solid object, but if you have a significant weight, it will compress a little bit. Maybe not something noticeably, certainly not visibly, but there will be some compression there. And Young's modulus is kind of a measure of how compressible that is. So again, we don't have to worry about the details, but that's just what it is. And again, something you'd look up. Like for concrete, you look up Young's modulus for concrete. Or whatever material you're looking for. And then rho, that is the mass density. So that'd be like kilograms per cubic meter would be the basic SI units. A more common unit for density would be a gram per cubic centimeter, and that's because water is defined, or, well, like a gram was defined so that ideally water would have a density of 1 gram per cubic centimeter. Now, it's difficult to define things that way because water is never totally pure, so it's not a very good way of measuring things, but that was the initial idea. So it's good to compare things, like water, 1 gram per cubic centimeter. Something like a rock might have like 3 or 4 grams per cubic centimeter. I'm going to write down one more. That would be a liquid, where the speed now this has a kind of impressive name. Well, it looks like bad, but B with a subscript AD. B is called the bulk modulus. And this AD, that stands for something called adiabatic. So, adiabatic bulk modulus. Now, the bulk modulus in general, whether it's adiabatic or not, we'll talk about what that means in a minute. But the bulk modulus, it's kind of like for a liquid, how compressible is a fluid? Or a liquid. Now, fluids would include gases as well, but so like how compressible is like if you apply pressure to a liquid, it will compress. And the bulk modulus is a measure of how compressible that fluid is. Kind of like Young's modulus for a solid, bulk modulus would be for a liquid. Now, what does this word adiabatic mean? And that means that there's no heat exchanged. And you'll learn about that if you take 122. You'll talk more about this adiabatic in a lot more detail. But it means there's no heat exchange. And that's something that can actually happen when you compress a fluid. Like say you have a fluid and you compress it, it's going to tend to heat up. And waves in fluids involve compression. However, there's really no significant heat exchange in waves because they move so quickly. Like you compress it and then it goes back to normal so quickly that there's no time for a significant amount of heat to exchange. To flow like into the fluid or out of it, or like into like the part of the wave from the surroundings. And so that's why we use this adiabatic bulk modulus. So if we had like a very slow wave where you compress things extremely slowly, then we'd get a different result. But just like a wave that's propagating in a fluid, they move so fast that that just doesn't happen. So we use the adiabatic bulk modulus. And the main reason, these are all in the notes, and we're not deriving them. The main reason I wrote them all down, though, is they all look pretty similar. Here on the bottom, here we have a density. Oh yeah, rho is the same here. Mass density, kilograms per cubic meter. So here we have a density, that's a density as well. And for a gas, well, we just have like the mass of the particles, kind of related to density at least. Gases don't really have a fixed volume, but it's always like a density or a mass on the bottom. And on top, it's always like a property of the material, like the tension in the string. Here, these are like how compressible a solid or liquid is. Like the gamma depends on what type of gas. And so there's a lot of similarities. And there's actually a more general formula you can write down for the speed of a wave, but we're not going to bother with that in this class. Talked about, this was a much longer video than I wanted it to be, so I will stop here. But basically, I believe we've covered chapter 16, or at least most of it. I don't remember if the next topic is in this chapter or not. Okay, actually The next topic we're going to talk about is intensity of a wave and the Doppler effect. Those are also chapter 16. But we covered a big part of this, so we will stop here.